Did E.A. Milne predict the detection of the microwave background radiation? As it happens, you can go and see for yourself because the text is available on archive.org, and you can look in Note 7 of the appendix to see the apparent brightness of a receding nebula. Now, Milne predicted a spherical isotropic receding nebula. However, the particle density of this nebula, he thought, should go to infinity, so it occurred to him that if it were hot and sending out light, that we should, contrary to observation, be seeing an infinite intensity light rather than no light at all. So his explanation is not focused on showing there will be a cosmic microwave background, but rather, how is it possible that the cosmic microwave background is finite in a model where there are an infinite number of particles? So with that in mind, let's begin. In order to show that the simple kinematic model gives a continuous background of finite intensity, it is necessary to have a formula for the apparent brightness of a receding object as measured photometrically or spectroscopically by a given observer at a given epoch of his experience. Let me give you my current impression of what Milne means here using a space-time diagram. We'll start with the light cone, starting from x equals 0 and at t equals 0, and expanding outwards at the speed of light, x equals ct and x equals negative ct. Then we'll have a nebula surface. That is, we can pick out any region of distant gas, which in Milne's model is going less than the speed of light, x equals vt. Then we have an inertial observer whose coordinate system defines this space diagram. So he's stationary, of course, within the coordinate system that his velocity defines. So that line would be, the line of the observer would be x equals 0 or 0t. So the luminosity of an object such as a nebula, that's this x equals vt line, may be supposed to given as a function of local time. So local time, that would be somewhere over here. So this point in time was now. Then actually this whole line would be local time. The same function for all nebula on average. I think I am reading the wrong sentence. I'm sorry. Let's go back. Here we are. It is necessary to have a formula of the apparent brightness of a receding object. So that receding object is this greenish one, as measured photometrically or photometrically by a given observer because that light is going from, or this is the light that he is experiencing at this moment. It's stuff that is coming from all distances at the speed of light from all of his surroundings. Now I can read that next sentence. The luminosity of an object such as a nebula may be supposed given as a function of local time, the same function for all nebula on the average. Okay. Now, the local time of all the nebula is going to be marked out on this diagram by hyperbolas. C tau squared equals ct squared minus x squared. And so tau equals square root of t squared minus x over c squared takes the form of concentric hyperbola. I'll call them concentric here because they're kind of similar to the concept of concentric circles, in the same sense that increasing circles or concentric circles are marked by increasing r. These concentric hyperbolae are marked by increasing tau. And that tau here is the local time. And it's the same function for all nebula on average, which means that the age of a nebula here, let's say the age of the nebula here is the same as the age of the nebula here. And the age of the nebula here is the same as the age of the nebula here. So we're discussing a luminosity of tau, a function. Where does it say luminosity? The luminosity of an object. Luminosity of tau is some function which depends on the evolutionary optical history of the nebula, is entirely unknown. But it is sufficient to leave it as an undetermined function. The form of the formula for the apparent brightness. Okay, so this is luminosity absolute, and then the luminosity apparent. For the apparent brightness, will then show sufficiently well whether the background intensity converges to a finite limit in spite of the infinite number of luminous objects present. So this is going to be a function of tau and that recession velocity. The effect of that recession, of course, is to diminish the apparent brightness, for the recession dilutes the stream of photons in space as measured by the observer. So we'd say this is less than L apparent from an object of a particular time, a velocity of 0, and a distance is undetermined. This I should say here that distance equals vt. So this is the apparent luminosity of an object at 0 velocity at a particular distance, and this is not the luminosity of an object with velocity v that is also at a particular distance, but that distance is fully determined by that velocity. An approximate formula for the effect given at small velocities has been given by Hubble from physical considerations. But for our purposes of applying the result to velocities approaching that of the speed of light, an exact formula is required. The following is a revised version of the original investigations given by the author in Astrophysical Journal 74, 71, 1931. Let's start that over. An approximate formula for the effect valid for small velocities has been given by Hubble in Astrophysical Journal 74, 71, 1931. From physical considerations, but for our purposes of applying the result to velocities approaching that of light, an exact formula is required. The following is a revised version of the original investigation given by the author in Zeit für Astrophysik 690, 1933, which has been confirmed by another method by A.G. Walker in MNRAS 94-162-1934. He then says, as brightness is measured in energy units, it is necessary to depart somewhat from a purely kinematic treatment. In particular, he's going to be discussing the brightness in terms of watts per steradian per square meter. No, more than that, actually what he does is spectral radiance in frequency by the watt per steradian per square meter per hertz. Radiance is useful because it indicates how much of the power emitted, reflected, or transmitted or received by a surface will be received by an optical system looking at that surface from a specified angle of view. The solid angle, which is measured in steradians, which is a square radian, the solid angle of interest is the solid angle subtended by the optical system's entrance pupil. For instance, the eye is an optical system. So if I had the object over here, it would emit an amount of light that was measured watts per meter squared. And then when the light got to your pupil, it would, whatever came in here, would be aimed down here at your optic disc, and that is going to be that circle has a measure of, well, measured from this point, you could measure an angle, and that angle kind of creates a solid disk whose dimensions is measured in steradians or square radians. So again, the solid angle of interest is the solid angle subtended by the optical system's entrance pupil, subtended from, and it should include from the optical system's, from the point of view of the optical system's detection coordinate. So since the eye is an optical system, radiance and its cousin luminance are good indicators of how bright an object will appear. For this reason, radiance and luminance are sometimes called brightness. This usage is now discouraged. The non-standard usage of brightness for radiance persists in some field, most notably laser physics. Our general method is to begin by considering a nebula at rest and an energy receiver in motion relative to it. So this is the location of the receiver, and this is the distant nebula, and the light here, or this is the, he's got it pictured as, it looks like it's just an angle measured in radians, but this is actually supposed to represent a solid angle, d omega prime. Alright, so in the first portion, we're imagining a nebula at rest and a receiver in motion, which is going to be seeing, so the receiver is going to be seeing, say, this light and then this light, and that's t and x. Then we transform the intensity at the receiver, measured by the particle observer on the nebula, into the intensity, okay, so measured by the receiver. So we'll do a Lorentz transform, considering the nebula and receiver coming like this. And so we'd be looking at, say, this and this. Okay, in our space-time diagram. The optical properties of the nebula are supposed given, however, in terms of the unit appropriate to an observer on the nebula, as this gives the standard behavior of the nebula. So, watts per meter squared per frequency, I think optical properties of the nebula are given in terms of the units appropriate to the nebula, as this gives the standard behavior of the nebula. We have, of course, to express the result in terms of the epoch at which the observation is made in the experience of the observer at the receiver. Now, I'm thinking that watts per meter squared per frequency, all of these things are properties of the nebula's emission, but the per steradian, I'm not quite sure. That's going to change a bit. This is definitely an observer-dependent quantity, I think. That solid angle in which the nebula is viewed. We have, of course, to express the result in terms of the epoch at which the observation, I think he means observation is made, epoch at which the observation is made, which is right in here, in the experience of the observer at the receiver. So we're going to use this time, but we'll be using an observation of an event that is back here. An event, the watts per meter squared per frequency, given in terms of the units appropriate to an observer on the nebula. That would be here, as this gives the standard behavior of the nebula. And the result in terms of an observer when the epoch at which the observation is made in the experience of the observer at the receiver. For convenience, we consider first the case of any uniform relative motion of source and receiver, not necessarily one of pure recession. Primed symbols refer to B's measures. B is the receiver here. Let ds sub naught prime be a radian. I'm sorry. What? Oh, I goofed. Wait. Wow, yes, I goofed. This is the receiver, and that is the nebula. For convenience, we consider first the case of any uniform relative motion of source and receiver, not necessarily one of pure recession. Prime symbols refer to B's measures. Let ds sub naught prime be a radiating surface centered at the point B with its normal in the direction of a unit vector n sub naught prime. So for convenience, we consider first the case of any uniform relative motion of source and receiver. Here is the velocity of the receiver. Not necessarily one of pure recession. Primed symbols refer to B's measures, the radiating surface, and let ds sub naught prime, right here, be a radiating surface centered at the point B with its normal in the direction of a unit vector n sub naught prime. Let ds prime be a receiving surface whose center at the epoch t prime in B's experience, i.e. at time t prime by B's clock, is at the point A. So from a space-time diagram I drew a little bit ago, that would be point B, and this would be point A, where the emission signal arrives, I think. So question is, did he say when the receiver is at point A? He said it's epoch t prime in B's experience. Did he say it is this intersection where the beginning of the beam actually reaches the receiver. I'm pretty sure that's what he means. This would be t prime, and this would be t prime plus dt prime. The times at which, or maybe it's this is t prime and this is t prime plus d prime. But he says that that is the point in A's experience. So I'm thinking he forgot to say when the receiver is at point A. In any case, this video is getting pretty long, so I will continue in another video and bid you farewell for now.